In this lecture, I want to take a look at AVL trees, which is one balanced tree implementation we want to study. AVL trees are balanced based on a very simple condition. For each node in the tree, the difference between the height of the left and right subtrees may differ by no more than 1. When we say left and right subtree height, let's see what we're talking about here. The height of the subtree is the longest path from root to leaf. Thus, from any path from 9 on the left-hand side, there are 2 paths, from the 9 to the 6. The other path is from the 9 to the 1. There are 2 leaf nodes along the left-hand side. So the largest number of edges along the paths, the maximal number, is the subtree height. Therefore, the height of the left side of the 9 is 3. This is the longest path. It's 3. On the right-hand side, there's only 1, and the height is 1. Therefore, the difference is greater than 1. The difference is 2. The 9 violates this AVL tree condition. So you can think of each node as a subtree all its own, and each one has a height left and right of its own subtree. So here with 1, the height is 0, 0. This is the case for all leaf nodes. The height of the left and right subtree are 0. Similar for the 6 and the 11. For the 3, the left height is 1, 0 on the right. The 5 has 2 on the left, 1 on the right. So the 9 here we have 3 on the left and 1 on the right. This violates the AVL condition, so the 9 must be rotated, and you will always rotate to the lighter side. You always rotate to the side with the shortest height. So we have 3 here, 1 here. So we're going to rotate the 9 to the right on the side with 1. So before and after, and as you can see, we have decreased the height of the tree by 1. We have made it bushier. So in this case, the 9 has to come down. Here, this 6 is to the right of the 5, but the 9 is going to come down and occupy that position. Therefore, the 6 can't be here anymore, but it can switch sides. The 6 is in between the 5 and the 9. Therefore, it can go on either side, so it switches from the right-hand side of the 5 to the left-hand side of the 9. So after the rotation, again, we can see this is met. The leaf nodes always have height 0 on the left, 0 on the right. The 3, height 1, 0. The 5, height 2, 2. The 9, 1, 1. Therefore, the AVL condition is met for every node in the tree. So for an insertion operation, you want to backtrack. Here we've inserted, when we insert a 1, we want to backtrack. So you will go along the insertion path, checking the height of each node in the tree. So the 3 has 1, 0. That's okay. The 5 has 2, 1. Again, that's okay. The 9 has 3, 1. Not okay. We have to rotate the 9 to the right. So as you can see, as we trace up the line, you can see what the heights are of each of these. And we discover that 9 is the one that's not okay. Now sometimes students get this wrong. They start at the top of the tree and start examining nodes. In this case, there's only one node that's bad in the entire tree, and so however you discover it doesn't really matter. But the reality is somewhat different. It may happen that there are multiple nodes in the tree that violate the AVL condition after an insertion. Therefore, it's important that you follow the same strategy when examining these. And the strategy is just this. Starting with the node you just inserted, backtrack along the insertion path, which is here. Checking each node and stopping when you find one that's bad, or if you get all the way to the root and the root's okay, then you're done. But you need not look at anything that's not along the path. For instance, there's no need to look at the 6 or the 11 because they haven't really changed. Therefore, you're only looking at the insertion path, and you do not start at the top, you must start at the bottom. This is a fairly small tree, and there's only one node that's out of joint here. There's only one node that's wrong. However, suppose the 3 were wrong. Suppose the 3 violated the AVL condition. If you had the 3 wrong and the 9 wrong, would it matter which one you rotate? Yes, it would. You must start at the bottom and work your way up and rotate the first node you find that violates the AVL condition. And once you do that, you're done. That is, a single fix-up step will always restore the tree to balanced condition. You will never have more than one fix-up step when you're doing an insertion into an AVL tree. A fix-up step is either a single or a double rotation. For instance, if the insertion path had been here and the 9 needed to be rotated, then we would need a double rotation because it's not a straight line. In this case, it is a straight line. A single rotation will do. So it takes a single fix-up step, and it must be the first node you find working your way back from the bottom that needs adjustment. So I want to do some simple examples here to help illustrate the point. So what I want to do here is look at the worst case scenario. I want to insert the even integers. So starting here, I'm going to insert a 2, and then I'm going to insert a 4. All right, backtracking. 0, 0, 0, 1, this is fine. Now I insert a 6. 0, 0, 0, 1, 0, 2. The 2 violates the AVL condition. It violates it because the height of the left subtree is 0. The height of the right subtree is 2. Therefore, we must rotate the 2. And we must rotate it the direction of the light side. That is the lower height. So this is an easy rotation. We have 4, 2, and 6. That is, we simply are pulling this 2 down here. Now inserting an 8. Again, we have to backtrack checking the height. We don't need to look at the 2. It's not even in the picture. The 8, 0, 0. The 6, 0 on the left, 1 on the right. The 4, 1 on the left, 2 on the right. So this tree is okay. No node violates the AVL condition. Now let's insert a 10. Again, backtracking. 0, 0. The 8, 0, 1. The 6, 0, 2. All right, now this tree is important. I want to call your attention to this. There are 2 nodes in this tree that violate the AVL condition. The 6 violates the AVL condition because it's 0 on the left and 2 on the right. The 4 also violates the AVL condition. So these 2 nodes both violate it. With the 4 we have 1 and 3. The 6 we have 0 and 2. Both nodes violate the AVL condition. However, if you rotate the 4, you've made a mistake. The node to be rotated is the first one you find along the insertion path. This is our insertion path. So backtracking, the first node you find, we take the 3 nodes. That is the node to be rotated, its child and grandchild. This is a straight line. Therefore, we're going to rotate the 6 to the light side to the left. We do this and we now have 4 and 2, which are unchanged. 8, 6, and 10. So this is the tree after the insertion of the 10. So we have rotated the 6 to the left. The new top is the 8. It becomes the right child of the 4. And so we have reduced the height of the tree accordingly. So I'm going to rewrite this over here. And erasing here. So I have rewritten this tree over here to get more room. So we'll continue on and we're going to add a 12. Is this okay? Let's look at it. We've got 0, 0, 0 here. The 10, 0, 1. That's okay. The 8, 1, 2. That's okay. The 4, 1, 3. This is not okay. The 4 is the node in the tree that is bad. So we're looking at this insertion path. We're looking at these nodes this time, these 3. That is, you take the node that's bad, the 4, 1, 3, its child and grandchild. So the 12 is the one that caused the problem, but we're not even going to touch it. It's left alone. These are the 3 nodes that are in play. So I'm going to have to pull the 4 down. Of course, the 6 is in the way, so it's going to have to switch sides. Right now, the 6 is the left child of the 8, but it will need to become the right child of the 4. So doing our rotation here, and I find it easiest to go ahead and write the new top or the new root node first. And that will be the 8. So I usually will do the 3 nodes involved in the rotation first to keep track of them and make it easier to avoid mistakes. I can look at these 3 nodes. It's a straight line. I know that 8 is going to be the new top. The 4 is going to go down, so I have 4, 8, 10. The 2 stays to the left of the 4. It doesn't move. The 12 stays to the right of the 10. It does not move. The 6, however, had to change sides. The 6 was left of the 8, but it now needs to be right of the 4. And there is our new tree. So the height is now 2 instead of 3. Now inserting a 14. And what happens here? 0, 0, 0, 1. The 12 has 0 on the left, 1 on the right. The 10 has 0 on the left and 2 on the right. The 10 needs rotation. So it's fairly easy to see what happens here. The 10 gets pulled down, the 12 promoted. So I'm just going to write the 10, 12, 14 pair here for simplicity. The 12 is the new top. The 10, the 14. Notice this tree now has height 2. Adding a 16. Okay, backtracking along the insertion path. 0, 0, 0, 1, 1, 2, 2, 3. This tree is fine. No node in the tree violates the AVL condition. So I'm going to now insert an 18. Backtracking, we have at the 16, 0, 1. At the 14, 0, 2, the 14 is bad and requires rotation. So again, for simplicity, I'm just going to replace these. We pull the 14 down. The 16 is promoted. All right, so now we're done. Insert a 20. Backtracking. The 18 has 0, 1. The 16 has 1, 2. The 12 has 1, 3. The 12 is bad. The 12 is the node that requires rotation. Okay. So we will start here. These don't change. However, what changes here? The 12 has to be rotated. It's 1, 3. It is 1 on the left. Therefore, the 12 needs to be rotated to the left. So the 12 is the node that requires rotation, and we want to look at the insertion path to identify the child and grandchild. So here they are, the 3 nodes involved. So now I will do this rotation. So we have here the 16, and then we have the 12. Here the 18, the 20 comes along for the right. It doesn't change, doesn't move. And so now where does the 10 go? It has to go where it was before. No switches needed. What about the 14? 14 was to the left of the 16 here. But to the left of the 16 is now the 12. Where does the 14 go? It has to go here. To the right of the 12. So again, between the 12 and the 16, we have the 14. When we pull the 12 down, it has to go in this position. Therefore, the 14 becomes orphaned, and it has to switch sides. It can either be to the right of the 12 or to the left of the 15 or the 16. Either way works. So now we have rebalanced the tree this way. Now I want to look at some double rotation, so I'm going to clear this pad, and we're going to continue on with a new example so we can look at double rotations. So imagine that I have 10, 5, 20, 15, 17. So this is my tree. I just inserted a 17. So backtracking to see which node is bad. 0, 0, the 15, 0, 1, the 20, 2, 0. The 20 is the node that's bad. Note also in this case, as well as the previous one, that the 10 is also bad. The 10 violates the AVL condition, but we're not going to touch the 10. We're going to backtrack from our insertion point and stop at the first node we find that violates the AVL condition, and that is the 20. The 20 violates the AVL condition because it's got 2 on the left and 0 on the right. Therefore, this is the node that must be rotated. It must be rotated the light side. It must be rotated to the right. Recall then that for a double rotation, you rotate the child the wrong way. Therefore, we have to rotate the 15 the wrong way. We're going to rotate the 15 to the left. So to do this is a two-step process. It's a double rotation. And now we rotate. We have 17 and 15. The 15 is rotated down, and that has the effect of pulling the 17 up. So now we have this intermediate step. This is the first of the two rotations required, and then the 20 gets rotated This way we have 10, 5, 17, 15, and 20. And the balance is now restored, and this tree satisfies the AVL condition. Let's do another example. Okay, so here is another tree. This was our insertion path. You may assume that the last thing inserted was the 12. So can we identify the node that needs to be rotated? Yes. 0, 0, 1, 0, 0, 2. The 10 must be rotated, and the 3 nodes in play are here. Now, it's true that the 25 also violates the AVL condition, but we're not going to touch the 25. You backtrack from the bottom and rotate the first one that is wrong, and then you're done. So, we see we don't have a straight line along this insertion path. We have a crooked line. We need to turn it into a straight line first before we can do the rotation of the 10. We do this by rotating the 15 the wrong way. So we have 25, 10, 30. Now we have 10, 12, 15. So notice that we have rotated the 15, pulled it down, which promotes the 12. So now we have a straight line here. Moreover, the median element, the 12, is in the middle, whereas before it was not. Here it's at the bottom. So rotating and pulling this up one is not going to help. It needs to be in the middle in order for it to do any good. So the second rotation, we can now go left with the 10. The first one, the 15, the wrong way, pulled the 12 up. So our final rotation is the 10 to the left, the light side, and we have 25, 30, 12, 10, and 15. And we have reduced the height by 1, and this is our balanced tree. Every node in this tree satisfies the AVL condition. 0, 0, check. 0, 0, yes. 1, 1, yes. The 30, 0, 0, yes. The 25, 2, 1, yes. Every node in this tree satisfies the AVL condition. So you will want to practice this to totally understand how it works, and there are some online tools that you can find doing a Google search where you can insert and watch the tree grow. And this is also recommended. It may be helpful for you. So this concludes our lecture on AVL trees.